like theoretical consideration. And so let's review a little bit of how we came up with our interval. So we start with f. Okay. So this is still our goal. This is always our goal. So the unconstrained minimization of f, and we do Taylor expansion. At the K-theoration. So this C is not the variable x, it's a point between x and x k theta, right? So once we take the gradient of this function, so we take the gradient, this is a constant, this is a constant, so we end up with, so let's recall the following. So if we take the gradient of E transpose x, and we take the gradient of 1/2 x transpose Qx, and Q is a symmetric matrix, so we'll get Qx. If Q is, so this is Q is symmetric. If Q is not symmetric, it will be 1/2 Q plus Q transpose. So then, by chain rule, so if we have x subtract xk iterate, so we'll get this is 2. Okay. So by this we'll get this is alright. So our hope is so this is our kth iterate. At our next iterate, we hope we can replicate this formula exactly. So we plug in. So we let x equals the k plus 1 iterate, so we'll get this. Okay. So if we let delta xk equals the difference between the k plus 1's iterate and the kth iterate, and we let delta g kth iterate equals the gradient of at the k plus 1's iterate subtract the gradient at the kth iterate. And then we can get our, so I don't know, fundamental equation of quasi-Newton method. That is, we want to find, yeah, I guess I'm really the only one who uses marker now. I mean, these new markers perhaps sitting for years in the so we want to find, okay. So we want to find H sub k plus 1 or create an efficient way of getting this matrix. So everything in this computational math and applied math, after all, we need to implement on the computer. So once we want to do implementation, one of the key factors is speed and efficiency. Okay, speed means it has to be fast, efficient means we need to use as few memories as possible. So so then we have, okay, so which this guy approximates the inverse of the Hessian. Okay. So the inverse of the Hessian, we subtract this to the left, and then we multiply the inverse. So then we'll have this fundamental rule of quasi-Newton. So after all, we're exploiting this rule to get an accurate approximation. We hope to get an accurate approximation for this. The reason is because once we get this, okay, so why we want to find this is because this inverse matrix will help us to get a good, okay, descent direction. Because if we can compute this exactly, it's the best descent direction. It's the Newton method. So it has quadratic convergence. So we can't get the best because it's too expensive, so we create some approximation so that we can approximate this efficiently. So now we have this equation. But we ignore one fact, okay? We ignore one fact is we took inverse of this identity. We haven't capitalized. We haven't taken advantage of the original identity, that is the Hessian, okay, itself multiplied. This is delta x. Delta x of k equals delta gradient. So this is an m by m matrix. So this is m by 1 vector, m by 1 vector. We have an identity of this as well. Okay. All right. So now here's the logic. So this guy is pretty clever. I would say, so there is some duality going on. Okay. So we have an updated rule to get hk plus 1. but we can create another matrix, this B sub k, okay, and B sub k plus 1, such that this guy, okay, so this guy approximates Hessian inverse. So keep this in mind. The notation wise is H approximate Hessian inverse, and B approximates the Hessian itself. Okay. So for example, for this HK plus 1 is derived using this update rule. But in the meantime, okay, let's look at this. So this is the Hessian. The true Hessian should satisfy this equation. So we can also update this B sub k using this rule. So this quantity and this quantity, this quantity and this quantity is straightforward to obtain. Okay. So once we create a rule to update this, so we can enforce. So this arrow here. So for example, from this HK. We can get BK in this way, and then we update. Sorry, this arrow should be on. Should goes up. Okay. All right. So here's the duality. So in the SR1 or single rank, this update, we used this identity to derive the update rule, okay? And then in the second order, in this DFB method, we still use this identity, but we want to keep the positivity of this matrix. So we want to create an update rule such that this matrix is positive. And in BFGS, which is the state-of-the-art quasi-Newton method, what happens is we want to create an approximation to the Hessian matrix itself so that we update this guy and we use the inverse of this guy. We use the inverse of this guy to better approximate this HK plus 1. Okay, so here's the idea behind it is we use extra information. So because after all, okay, so here's the logic is after all this HK plus 1 approximates Hessian inverse. It creates approximation. It uses one piece of information, which is this. Okay, so we use this identity to approximate Hessian inverse. There is another identity, which is this guy, which is duality, and we haven't exploited this. So the idea is the BFGS is we use an extra duality to better approximate Hessian inverse. But then in the end, you guys might ask me, okay, you told us the inverse is expensive to compute. Okay, the inverse is very expensive to compute. Here, inverse is very expensive to compute. So how this method is efficient? All right. So the answer is the following. So if we have a big block matrix, okay, and so A is an m by m matrix. A is M by M matrix. So this is M plus 1. We add one column and one row to this A. Okay? A inverse, we know. All right? Then what happens is this matrix, so A is some matrix inverse, we know, okay? And we add an extra column and row. We'll see in a moment. It's not just adding here, but also A is being added as well. So then what happens is this matrix, okay, its inverse can be exactly written down using A's inverse. Okay. So this is a very famous idea in numerical linear algebra. Okay. So it's called Schur complement. So Schur complement says, so we have this type of block matrix. This is A, this is C, this is B, this is B transpose. Okay. So if A, so the idea is this is pretty straightforward. So divide and conquer is one of the best ideas used in applied math. This whole matrix inverse is hard to compute, but A's inverse is easy to compute. Or say A's condition number is good. So what happens is we don't compute the whole inverse. Okay. We solve a block system, which is A inverse, and then we plug this in. For example, if this is U, this is P, okay. This is F, this is G. What happens is we solve the first equation. The first equation is AU times B transpose P equals F first, and then we plug in U in the second equation. Okay, we apply. So then what we get is the Schur complement equation. We apply iterative method. So next semester I will talk something about this. This is related to some state-of-the-art SVD method as well. SVD is the math behind the famous principal component analysis. But okay, so let's back to this problem. So our idea is this upper block, the inverse is known or easy to compute, or we already have from previous iteration. So what we want to do is we pad this matrix with one extra row and column, and we want to compute that inverse. So we have this famous formula, which is Sherman Woodbury Morrison identity. So lemma. Yeah, maybe I should wear a mask. So, okay. So first, A has to be invertible. So A is an M by M matrix, and A is invertible. All right. So and then we have U and V are two vectors in Rn. And such that, so 1 plus A inverse U this guy is not 0. So this is the number. So this is A inverse times U inner product with B. So then we get a scalar, and it's not -1. And then what happens is this matrix inverse, that is A plus U tensor product with V inverse. Okay. Remember in the single rank, in this SR1 or in even in the DFB, which is rank 2 update, the matrix is in this form. So it's like A plus a coefficient times this. So we derive this first. Okay, so, and then this guy's inverse. This is not approximation. This is exactly equal. Okay. So is exactly equal to okay. So this is a famous SMW identity, and I mean, we don't have to memorize it, so a more general version will be given as a formula sheet in the exam. I mean, but the idea is once we derive the proof of it, I mean, if we'll be working on, solving this type of system for many years, then this formula is very natural. Okay, so let's look at the proof. So let's consider the following system. That is so let's consider this block matrix system. So if we wanna visualize this system, it's like A is an m by m matrix. Okay. So B is an m by m matrix. So we pad this matrix system. So this U is an m by 1 vector. Okay. So V transpose is a 1 by m vector, and then we have this -1, which is a scalar. So it's like we enlarge this system by adding one more variable lambda, okay, by adding one more equation, this equation. So this equation is called, so this lambda is called Lagrange multiplier. And okay. So if we write down this system explicitly, what we will get is A, okay, so A times X, okay, this is our X, this is our lambda, okay, so A times X plus U times lambda. Lambda is like a scalar, keep in mind, lambda is a scalar. So this is not a matrix vector product, so we have to keep our so we have to keep our thought clear about the dimension of each vector. Okay. So this equals F. And then we have this V transpose X subtract lambda is 0. So we have this is V transpose X subtract lambda is 0. Second equation. So second equation, I mean, we done, so linear algebra, undergrad linear algebra using this row column rule. So in the cutting edge research, machine learning, other stuff, the block matrix still follows this rule. Okay, so if this is a matrix, this is a vector, it still follows this block row column rule. That is this guy times this guy plus this guy times this guy. Same thing. And then second equation implies lambda is V transpose X. Okay. Right. Now we plug back in lambda here. Okay. So we have this is A times X plus U V transpose X. Parentheses, okay, equals that. Remember the trick we used in quasi-Newton. So we have three vectors. Okay. We have, so we used to have this thing. UVX, okay. But this is also UV transpose X. We compute this first, and then we compute this. So in the quasi-Newton, we have this, and then we simplify it using this. So in deriving the Sherman-Woodbury-Morrison identity is we have this first, and then we want to write it in this way. So once we do that, UV transpose is nothing but U tensor product with V. And then this is an M by M matrix. So this is an M by M matrix. So this is an M by M matrix. And if this is an M by M matrix, and A is an M by M matrix, okay, so we can pull X out. So we have this is A plus U tensor product with B, X equals F. So if for a moment we assume this is invertible, then we can get X. Okay, so we assume this first. We don't know this yet, but later we will see this is indeed invertible. now let's recall our derivation. We have two equations. The first derivation is we solve for lambda in the second equation, we plug in the first equation. Now, how about we try solve for x in the first equation, and then we plug in the second equation. Why we can solve x? Because the matrix multiplying it is invertible. So we can solve for x. Now, what happens is we solve for x. Okay, in the first equation, this is your typical Schur complement trick. Okay. So let's just for a moment illustrating using this general problem. So for example, this problem is AU plus B transpose P equals F. And then if we solve for U, U is A inverse F subtract B transpose P. And once we plug it to the second equation, we'll get this is B times U plus CP is G. And this becomes B A inverse F subtract B transpose P plus CP equals G. And if we combine everything, okay, so this will be what's happening is B A inverse B transpose P equals what have I done? So let me still write this out. It's G subtract B A inverse F. Okay. So this guy is called Schur complement. Here it's exactly the same. So okay. So we solve for x in the first equation. X is so AX equals F subtract U times lambda, and we have this x equals A inverse F subtract U lambda. And we plug this in the second equation, we will get so B transpose A inverse F subtract U lambda subtract lambda equals 0. So now what we can see is we have this V transpose U. Okay, V transpose U is a scalar. So this is the nicest thing about it. So here we have V transpose. I have A inverse. Sorry, I have A inverse somewhere. Let me write this explicitly. So it's A inverse F subtract A inverse U times lambda. Okay. All right. Then we have this is V transpose A inverse F subtract V transpose times A inverse U times lambda, subtract lambda is 0. So now we isolate the term with lambda, right? So what we have here is, this is a number. So this term is V transpose A inverse U is nothing but A inverse U in a product with B. So now what happens is we plus these two terms to the right, then we rearrange a little bit. We will have this is 1 plus A inverse U V times lambda is V transpose A inverse F. So let me remind us, okay? We assumed this guy is not 0. So by assumption, this is not 0. If it's not 0, we can divide it to the right, and we have this lambda. So we have another expression of lambda. All right. And now, what happens is we have another expression of lambda. We can plug it back in the first equation again. So sounds like circular logic, but it somehow works. Okay, so we plug in back to the first equation. Okay. So AX plus U times lambda equals F. Okay. So now, if we plug it in, it's A times X. All right. Yeah, let me still write down this first. So lambda is this guy. So lambda is a number. Okay. So first we have to acknowledge that this is a number in that. So this is 1 by m matrix. This is m by m matrix. This is m by 1 vector. So it gives us a scalar. Okay. So we multiply this vector u. So we will get this is u. This is 1 plus A inverse u in a product with B, and on top is B transpose A inverse F equals F. So we're almost done. Okay. So what happens is we subtract this to the right, then we multiply A inverse on both sides. Okay. We know that A is invertible. So then what we will have is, so X, so we subtract this term to the right, then we multiply A inverse, then we will have X equals A inverse F, so we subtract this term to the right. Okay. right, subtract plus. Can I see my initial notes?
Yeah.
So I wrote this as plus, right? It should be minus. Yeah. So in the initial lemma, the plus on the right hand side, it's A inverse plus. It should be A inverse minus. My bad. Just change. Did I write plus? I did? Okay, sorry. So we already see it here. It's a minus sign. Anyway, so it's subtract A inverse U. Okay, 1 plus A inverse U inner product with V transpose A inverse F. So now we're going to play some magic. First, let's look at, so this is a vector, right? So this is a vector. So this is n by n matrix, n by 1 vector. So this is an n by 1 vector. Okay, so this thing is a scalar. All right. So we're going to rewrite things a tiny bit. Okay, so we're going to rewrite things tiny bit. We notice this is a scalar, so we don't care about the division term. So what we have is A inverse U times V transpose A inverse F. Okay. So this is this vector multiplied with this scalar. All right. So now we have this trick again. That is, so we treat this A inverse U and V transpose A inverse as vectors. This as one vector, this as one vector. So this equals A inverse U, okay, multiply with V transpose A inverse first, all right, and then multiply with that. So this is an n by 1 vector. So this is an 1 by n vector. So V transpose is 1 by n, and A inverse is n by n. Okay. Right? So remember this identity, X tensor product with Y is X Y transpose. Okay. Did I have asymmetric? It doesn't have to be symmetric, but yeah. Okay. So now if we write, oh yeah, that's right. Okay. So now A inverse U V A inverse is equal to A inverse U, so we rewrite this as a single vector's transpose, okay, is A inverse V transpose. So this is V transpose times A inverse transpose. Do we have to assume A is symmetric? It shouldn't have been symmetric. Somehow I have symmetry here. Yeah, let me find let me rederive it somehow. But why do we need symmetry? We need symmetry here. Let me just put question mark here, okay? Let me try to correct my lecture notes. Symmetric. Let me just put question mark here. Okay. So this step needs symmetry, but I don't think we need symmetry in the SMW formula. So once we do this, we can see, so x equals A inverse F minus, okay. So we kind of isolate this guy with this guy, then multiply with the F. So what happens is, this is 1 plus A inverse U, inner product with V, and this is A inverse U, tensor product with A inverse V. Okay. So we have x is A inverse minus A inverse U V, A inverse U tensor product with A inverse V. Yeah. So now let's compare the two formula. So we have an m by m matrix. So this is an m by m matrix. This inverse is an m by m matrix. So we have this vector x equals an m by m matrix times f. In the meantime, x is an m by m matrix times f. F is an arbitrary vector we choose. The arbitrary s of f. So we have shown the S7W identity. Now let me figure out, I don't think we need symmetry in A, but somehow over there. We only need A to be invertible. Let me check Wikipedia really quick. Yeah, we don't need base symmetry. So how can we change? This part is correct. Okay. So I think yeah. Let me just don't enforce symmetry. Let me change this to minus t. Okay. So A minus t, A to the minus t is basically A transpose inverse. So because A is invertible, A transpose is invertible. Then we have this is minus transpose minus transpose. Yeah. Okay. So then with this identity, what we can do is let's recall the formula. So let's recall BFB update rule. For HK plus 1. So this is our DFP update rule, which is the rank 2 update rule, and we've shown that if HK is positive definite, this update rule will maintain the positive definiteness of HK. So now what BFGS does is, because of the duality diagram we plot here, okay, so we have a new rule. So what happens is, we simply, in the new rule, what we do is we change HK to BK and the change in the gradient to the change in X. Okay. Let me use this color marker to denote the difference. We simply switch X and G. So by duality, we can create this update rule. So next, so let me. Yeah, the derivation is too long. But let's do it next time. So in next lecture, so we'll use SMW formula and this update rule to create a single update rule for HK plus 1 that takes advantage of this duality and to get a more accurate approximation to the inverse of the hash. So that's it for today. So I'm not quite in the in a good condition to lecture, but yeah.
So it's like we approximate the BK for the HK, right? Or is it like
so BK is like approximation of HK inverse.
And HK is an approximation for like delta
BK
2.
inverse. So they're like alternating.
I mean, like because you said, like since it's too hard to just like define or calculate the delta to zeta, we just like some sort of like approximate to HK, and HK right now is like going to approximate to BK. Is like we're getting far and like putting
so yeah, okay. I may have know your question is what the SMW formula try to play in the role in this type of thing is. So this formula is by duality. Okay, next is we use SMW formula. So these are two update rules. So this is actually another quasi-Newton method by this single formula. So the BFGS is we combine these two and SMW formula to create a single update rule for H that somehow the duality is also used. Okay, so that's the idea. But it's a long derivation.
You mean after single update, you put for scheduling time update and two update? Is it means two updates?
No, we'll create a single formula like this,
And then
using SMW formula.
yes, then for two update What?
No, we don't have to, we don't track BK. BK is like a hidden matrix that we used in our derivation, but we never explicitly computed.
You automatically get update.
Yeah, so we have this formula, but we don't explicitly use this formula.
So
We just want to make our method more efficient. We want to create a single formula like
that
this.
means we always use the second term and repeated it. I mean the first one. The
So
first
we want
one.
to create a formula that the second formula holds,
What this one?
but using the form of the first one.
Oh.
I'm finished.
Oh, really? Wow.
Thank you. Thank you.
I don't see. Yeah.